Okay, in a discrete metric space, a sequence can converge to a point. In a discrete metric space, a sequence converges to a point only if it is an eventually constant sequence. If the sequence is eventually constant, only then it will converge with respect to the discrete metric space, with respect to the discrete metric, or it has an eventually constant subsequence, otherwise not. So in other words, a sequence may not convergent in a discrete metric space. It will converge only if it is an eventually constant sequence. Number two. Second is that the convergent of the sequence in a metric space X depends on the space X, in which space we are considering the sequence, and with respect to which metric we are considering. So the convergent of the sequence depends on both the space as well as on the metric. So for example, let us consider an example. Here is we consider the sequence xn is equal to 1 over n. Okay, so this is the sequence of real numbers, and real number is cubed with the usual metric. Okay, and then we know that this sequence approaches 0. Okay, the xn converges to 0 as n tends to infinity. This is well known. Okay, hence we consider the, so now if we consider the metric space x is equal to 0, 1. Now the important thing is that keep in mind, we are with the usual metric. So I am not considering x as a subset of R. Okay, I am considering X as a whole space. So if you consider X as a whole space with the usual metric, then you will see that this is a subspace of R. And in that case, of course, this would be a sequence. Okay, so you can start from not from n is equal to 1, but n is equal to 2 you can start. So this sequence, then this sequence where then the sequence this, okay, will converge with respect to the metric which is the restriction of the usual metric, but it will converge to 0, but 0 is not in this set. And therefore, the sequence, this sequence will not converge to any point in this set. So we cannot say that the sequence xn converges in X. Okay, and therefore xn is not a convergent sequence in this case. So in this case means in the metric space X is equal to 0, 1. Now let's take suppose you have a sequence of functions, sequence of real valued continuous functions defined on a closed interval AB. So this is a sequence of functions in C01. You have seen we have defined several kind of matrices on C01. One was the max matrix, another was the integral matrix, and then several others. So let us take and here is we are considering Fn is defined, Fnt is equal to e raised to the power minus nt for all natural number n. Okay, so we define this matrix, and then we will see that this sequence of functions converges to 0 function. Okay, converges to 0 function with respect to the integral metric or with respect to the D1 metric. Okay, how it is? You can see that D1 metric D1. Okay, you remember that we have defined the D1 or D, you can say that D1 Fg is equal to the integral. I am taking from A to B mod of f of x or f of t better. You take so f of t minus g of t dt. Okay, so this is the metric D1, and now here is GT is equal to 0 and f of t is equal to e raised to the power minus nt. Okay, substitute these values and a is equal to 0 and b is equal to 1, and then you will see that this d1 fn 0, so fn, so here is equal to e raised to the power minus nt and g is equal to 0, so 0. Now you integrate it, you will get 1 over n, 1 minus e raised to the power minus n. So as n tends to infinity, this will tend to 0, and therefore the whole thing this converges to 0 or tends to 0. Okay, so it means that the fn converges to 0. Now, on the other hand, if we consider the max matrix means we have defined the max matrix, okay, or D infinity matrix. We can say that here is D infinity matrix is equal to maximum of mod of f of t minus g of t, and t is in the this one. So here is you can see, if you look, then fn, so f with respect to d infinity fn 0, so it is equal to, because this is your g, okay, so here you will get e raised to the power minus nt. So the maximum of this, when t lies maximum over t in the closed interval, the maximum of this is equal to 1. So this, okay, the distance between f and 0 does not converge to 0, but it is equal to 1. Okay, so this does not converge to 0, but because it is equal to 1. So you can see that this sequence xn of functions in continuous real valued functions defined on the closed interval a b, okay, and the sequence fn defined in this way, then this sequence with respect to the integral metric on CAB converges to 0, but it does not converge with respect to the max matrix or with respect to the sup matrix A on C01. So the convergence of the metric, the convergence of the sequence depends on the metric as well as on the space. Now, let us see here is, as you have seen in case of reanalysis, that a sequence can converge at most one point. A sequence cannot converge more than one point. So same holds in the case of metric spaces. So we have the result, a sequence in a metric space X cannot converge to more than one limit point. In other words, in a metric space, every convergent sequence has a unique limit. Okay, every convergent sequence has a unique limit. That is to say, if xn converges to x, okay, then x must be unique. So let us prove this one, very simple proof. So let xn xd be a metric space and xn be a convergent sequence in X. Suppose to the contrary that xn converges to two distinct points x and y. Okay, then by the definition of the convergent of sequence, for every epsilon positive there exists positive integer n1 n2 such that d xn x is less than epsilon y2 for all n is greater than n1, and d xn y is less than epsilon y2 for all n is greater than n2. Okay, keep in mind here is this n is also depending on this point. Okay, n is also on us, so this is depending on this one. So you will get this one. Now what we can do, we can take capital N is the maximum of n1 and n2, and using the triangle inequality, then we can say that dxy is less than or equal to dxn x plus dxn y, but this is less than epsilon by 2. Okay, for all n is greater than capital N, because N, for this N is greater than N1 and capital N is the maximum, so it is also holds good for N is greater than capital N. And this is also in the same way, this is less than epsilon by 2, so dxy is less than epsilon. So this dxy is strictly less than epsilon. So as epsilon approaches to 0, okay, what will happen? This will approach to 0, but it is greater than or equal to 0 and it is less than or equal to 0. So x must be equal to y, and there, so x is, hence the limit is unique. Now, what is the concept of a bounded metric, bounded sequence? Okay, we have seen that a metric space is bounded, or a subset of a metric space is bounded if its diameter, okay, if its diameter is finite. So here is a sequence in a metric space is said to be bounded if the range set of the sequence is bounded. Okay, so there are two things keep in mind. One is you always write, suppose you have xn, okay, xn means the element of the sequence are x1, x2 and xn and so on. So these are the component of the sequence. But then the same way you can consider this as a set. So this whose elements are x1, x2, xn and so on. So if we consider this as a set and this set is bounded, then we say that the sequence is bounded. That is to say, in other words, you can take that d of xn and xm. So you take any xn and any xm, any two elements of this set. Xn is the element of this set. So the distance between any two element, okay, the supremum of the distance is finite. So you take any two element, so that must be less than or equal to some constant k. So then we say that the sequence is a bounded sequence. Okay. Now, in a metric space, every convergent sequence is bounded. In a metric space, every convergent sequence is bounded. So, let xd be a metric space and xn be a sequence in x such that xn converges to x. Okay, and then we will prove that this sequence is bounded. This sequence is bounded means you take any two element of this set and prove that the distance between any two element of this set, okay, the range set of the sequence is finite. Okay, then because xn converges to x, so there exists a positive integer n such that for every epsilon positive, or we can take epsilon is equal to half. So for there exists a positive integer n such that dxn x is less than f, a half for all n is greater than n. Now let us set r is equal to maximum of half n this, okay, for all n runs from 1 to n. All this n before, okay, before this capital N, here this all this. So let us take half and this one, and then we will see that dxn x is less than or equal to r for all natural number. Okay, by the triangle inequality you can see that instead of taking x, we can take xm, any element of the range set of the sequence xm. So xn and xm is less than or equal to this thing by the triangle inequality, that dxn x plus dx xm. This is less than r, again this is less than r, so the whole thing is less than 2r. It means that we have taken any two element of the range set xn and xm, and we have seen that the distance between dxn x xm is finite, and therefore the range set is finite, and the range set is finite, and therefore the sequence is bounded. Okay, so this way we can prove that every convergent sequence is bounded. Now what about the converse? Can we say that every bounded sequence is convergent? No, this is not true. Okay? So, in a metric space, a bounded sequence need not be convergent. For example, you can consider the set x is equal to R with the usual metric space and take the sequence xn is equal to whose element minus 1 raised to the power n. So, you will get your terms are 1, minus 1, 1, minus 1, 1, minus 1. And this sequence is bounded below by minus 1, bounded above by 1, but it is not convergent. Okay? So, this way you can see that a bounded sequence may not converge to a point. Now, we have a very important result. What is the result? Result is this. Suppose X D be a metric is a metric space and A is a subset of X. A point X is called a limit point of A if and only if there exists a sequence of points of A, none of which equals X such that Xn converges to X. What does it mean? Okay, let's see here is suppose you have a metric space. Okay, this is your X and here you have, suppose this is your set A. Now let me take this is your point X. So this point X is called a limit point of A if every open sphere with center at X intersects with A, or you can take X is any point X in X intersects with A. Now this X is the limit point of A if a sequence x1, x2 and xn, okay. So this sequence of points of none of which such that xn converges to X. So if there exists a sequence of points of X such that this sequence converges to X, then this X is the limit point of this. Or if X is the limit point of X, then there exists a sequence of points of A such that Xn converges to X. So this let's prove this one. Okay, now the second part is that A set A is closed if and only if every convergent sequence of points of A has its limits in A. Okay, this is very important. Important that a set A is closed if and only if every convergent sequence of points of A, okay, has its limits in A. For example, suppose you have a sequence xn in A and xn converges to X, and if this limit point is in A, then A is closed. And if A is closed and if you have a sequence xn in A that converges to X, then X must be an element of A. So this way you can prove the closeness of a set in terms of sequence. So this is a very important. So let's say here is the proof. So the proof for this, let X be a limit point of A. So suppose X is the limit point of A, and then we will prove that there exists a sequence, okay, points of A that converges to X. So we will have to construct, to prove this statement, we will have to construct the sequence Xn which converges to X. So since X, we are assuming that X is the limit point of X. So X is the limit point of X, and therefore then the open ball with center at X and radius 1 intersection A is non-empty, okay, other than X. And so because this is non-empty, so we can take a point x1 in this set. So we can take x1 in this way, in this set. And then again we can have a open sphere with center at x1 and radius half. Intersection A is non-empty. Okay, and then we can choose the point x2 in the same way. So likewise, the points x1, x2, xn can be chosen such that xie lies in the open sphere with center at x and radius 1 over I minus x intersection A for all I runs from 1 to n. And still you will see that S 1 over n plus 1 x, open sphere with center at x and radius 1 over n plus 1, intersection A is non-empty. So we can choose xn plus 1 in this set, xn plus 1. By repeating this process infinity many times, so we will get a sequence, sequence of elements of x. Okay, all the elements of xn are in A, and they xn, because xn is not equal to x, so xn is not equal to n for all natural number n. Okay, now we want to prove that this sequence converges to x. So for that, let epsilon be given and n be a positive integer such that n is greater than 1 over epsilon. Then you can see that because xn lies in as 1 over n x. Okay, so it means that xn lies in as 1 over n x. But from here we can say that 1 over n, so you can say this is a subset of S epsilon x for all x n is greater than capital N. It means that all the elements of this sequence lies in this open ball with center at x and radius epsilon, and therefore xn converges to x. So xn converges to x. Okay, let's take the converse part. So the converse part is assume that there is a sequence xn of points of x, none of which equals x, such that xn converges to x. Okay, then we will have to prove that x is a limit point of A. Okay, we will have to prove that x is the limit point of A. Okay, so for that, for every epsilon greater than 0, okay, xn converges to x. Okay, so for every epsilon greater than, there exists a positive integer n such that xn lies in as epsilon x, open ball with center at x and radius r. Okay, and therefore this set is non-empty. It means what? It means that x is the limit point of A. So this is the proof. To prove the second part, to prove that the set A is closed if and only if every convergent sequence of points of A has its limits in A. So to prove that, suppose that A is closed, okay, and xn is the sequence of points of A which converges to a point x in x, then we will have to prove that x is an element of A. Okay, then we have to prove that. If the range set of the sequence xn is infinite, then it follows from part A that x is the limit point of this set. Okay, and since A is closed, the x must be an element of A. On the other hand, if the range set of the sequence xn is finite, finite, that is to say xn is equal to x for all n is greater than n. Okay, then xn, since xn is convergent sequence, so the range set is finite, so this must be equal to x, and since each term of the sequence belongs to A, so x also belongs to A. For the converse, assume that every convergent sequence of points of A converges to a point of A. Now we show that A is closed by showing that it contains all its limit points. So let x be a limit point of A, then by part A there exists a sequence xn of points of A, none of which equals x, such that xn converges to x. But by the hypothesis, x must be an element of A, hence A is closed. Okay, So this way we can prove that the sequence, we can prove the statement of the result. Let us take an exercise. The exercise says that show that the limit of a convergent sequence of distinct points in a metric space is a limit of the range set of the sequence. Okay, so let xn be a sequence of metric space such that xn converges to x, and let A be the range set of the sequence xn. Okay, there is a, so here is a sequence of distinct point, keep in mind. Okay, so this is the range set of this sequence. Then we have to show that x is a limit point of A. So suppose that x is not a limit point of A. X is not a limit point of A, then there exists, yesterday I have showed you how to write the negation of a statement. So keep in mind, you should have the definition of a limit point and then you write the negation, because the limit point, the definition for every open sphere centered at x, every open sphere. So the negation is that there exists an open sphere as epsilon x, that is open sphere with center at x and radius epsilon, such that the S epsilon x minus x intersection A is empty, because in the definition of the limit point it is non-empty, so here it's empty, and in the definition of the limit point here is for every open sphere, so here is there exists an open sphere. Okay, and then we can see that this contains no point of A other than x. Okay, you see here is because this minus this, so this contains, A contains no point, this contains no point of A other than x. Now since x is the limit point of the sequence, so for each epsilon positive there exists a positive integer n such that this is true, or you can say xn lies in the open ball with center at x and radius epsilon for all n is greater than n. Okay, but this is the contradiction, because we have seen that there exist open sphere such that they are not empty, but here is we are saying that this contains no point of A other than x, but here we are proving that this open ball with center at x and radius epsilon contains xn for all n is greater than n. So this contradicts with this one, and therefore what we assume that x is not a limit point, it is not correct. X is a limit point of A. So this way we can prove that x is a limit point of A. Now another exercise here is let x be a metric space if xn and yn be sequences in x such that xn converges to x and yn converges to x, then prove that dxn yn converges dxy. Okay, so very simple, just we have to use the definition and the triangular inequality, nothing else. Let's see how we can prove this one. So because xn converges to x and yn converges to y, so for each epsilon positive there exist positive integers n1 and n2 such that dxn x is less than epsilon y2 for all n is greater than n1, and dxm x is less than epsilon y2 for all m is greater than n2. Now we can choose capital N is equal to maximum of n1 and n2. Then we will see that for all nm greater than capital N, we have mod of dxn yn minus dxy, because we want to prove that this converges to this, it means that mod of, this is your real number, so mod of dxn minus yn minus dxy converges to 0. This we want to prove that. So here is by using the triangular inequality, this can be written as mod of dxn yn minus dxn y plus dxn y. So we have added and subtracted this term and used the triangular inequality. So, and then we will see that this is less than or equal to, okay, dy and y, and this is less than or equal to dxn x. But this is less than epsilon y2 and this is less than epsilon y2. Okay, So this is less than epsilon. It means that the mod of this minus this less than epsilon, it means that this dxn yn converges to dxy. Now, finally, I give one more last exercise here, that we are considering the metric space C01, okay, and a sequence of functions fn where fn x is equal to x raised to the power 1 over n. And then the question is that show that fn converges to 0 with respect to the metric d1. With respect to the metric d1 means with respect to the integral metric, while it converges to 1 with respect to the metric d infinity. Okay, so it converges with respect to d infinity. So let us take since x raised to the power 1 over n is less than or equal to 1 for all x lies between 0 and 1. And so we have d1 fn 0, it is equal to 0 to 1 x raised to the power 1 over n dxn, because in this one this is equal to mod of fn x minus 0. Okay, so you will get this one, and then after calculating the integral you will get 1 minus 1 over n plus 1. So as n tends to infinity, this tends to 0, so this is 1, so 1 minus 1 is 0, it is equal to 0. The other, for the max metric or the sup metric, what we will get? We will get d infinity fn 1, okay, which is equal to, here you got 1 and fn is equal to x raised to the power 1, and now because this is less than or equal to 1, okay, so the supremum of this, so this is less than, so this could be equal to 0, so the supremum is equal to 1, so this is 1. So you can see that the sequence f and x is equal to x raised to the power 1 converges to 0 with respect to the metric integral metric, and it converges to 1 with respect to the sup matrix or d infinity matrix. So it depends so which kind of the metric we are considering. Okay, so now I stop over here. Thank you very much.